Welcome to a lesson with Dr. Powell. Let's take a look at how we can think about integrating on a surface, analogous to what we had when we were integrating along the curve instead of a coordinate axis. So we're going to be integrating on a surface in contrast to integrating on the XY plane. How do we think about it? Well, if we take a little piece of the surface, we can split that up a little bit. That piece of the surface has a projection onto the XY plane. It also has a projection onto the ZX plane. It also has a projection onto the YZ plane. So we have different projections onto these. And when it projects onto them or casts a shadow, it's again a region, but this is a region in the XY, a region in the ZX, and a region in the YZ. How do we integrate along this surface? Well, we simply add three different integrals together. Integral 1, 2, and 3. These integrals are going to be with respect to x and y, or zx or yz. They'll be double integrals. So we'll have three double integrals that we add together. But I will write them like this, with a dx, a dy over here. Perhaps I'll write and then over here, I'll do a dy dz, and over here, I'll do a dz dx. So what I need is a weighting or something to throw in right here. Now, analogous to what we did for a curve, we again have a vector field. Notice how we have three different components. And we're going to allow these different components to be functions of x, y, z, just as a point on the surface is given by an x, y, z coordinate. Of course, those coordinates might depend on some kind of parameterization or might be functions of something else in order to make it so we're on the surface. But what we're integrating fundamentally will be thought of as a vector. Because we have these three different projections. So we can think of a vector field as follows, such as f, and perhaps this is a function of, maybe we'll have fxy, z actually. So this is in space at a given point. You're going to have a component here for the x, a component for the y, and a component for the z. And it's going to be a new vector for each point. And you can picture them as being like arrows like this. Force fields, magnetic fields, other fields like that can be represented as follows, as a vector field. Vector fields are what we can integrate over a surface because we have these three varying and different components. Now, essential for this type of integration is orientation. How are things oriented? And what does orientation mean? Well, so an aerial projection, you have to be somewhat careful, because what if a surface, on one side of a piece of a surface, we would like the area to be positive, but on the other side, we'd like it to be negative. Now, knowing whether we're discussing the area on one side or the other has to do with orientation. How we're looking at it. Are we looking at it from one side or the other? Well, if we happen to look at our coordinate system and this is what we see an x and a y together, which could also be pictured like this, x, y. But no matter how we're looking at it, we're always thinking of y as being a counterclockwise turn from x. If we're seeing this, then we think of something with an x dx and dy is going to have a positive area. We're looking at it from the front side. What if we were to look at the picture and we happen to see something else? What if we saw a What if we saw a yx? Like that or like this. Then we'd know we'd be looking from the back side. And then we would want to consider negative area. There's an operator that we're going to use called a wedge product. We'll think of it as an orientation operator. Right now, notice how I wrote these in the order I have. I actually wrote these things in this order so that the orientation would give a positive area. You can double check it if you want and look through it. Z before X is important because we have a counterclockwise. Similarly here, dx, dy, and a dy, dz right here. So usually what we have when we integrate over a vector field, we have a couple different ways of writing this. We'll work through the details and examples to follow of how all these things fit together. But for now, let's just think about notationally what we see. If we have a surface, we could think about integrating a vector field, f, and then we dot it with this vector right here, which we'll label as dy dz, dz dx, dx dy, which this vector right here, we could label perhaps as, if we wanted to, as maybe a dA or maybe even a ds. Sometimes we do that if we're over the surface S. There's different ways of notating this. And we'll talk about the mechanics of this and what it actually means in later videos. But this is one way of thinking about it. And if you undistribute these doubles into one double, and you take the dot product, you're simply just adding, this is simply just another way of representing this. Or you could just undistribute the integrals here and think of just having a sum like this. Then what you're integrating is you're integrating something called a differential two form. Represented right here. Notice how you have your differentials. Now, normally in this differential, you use this wedge product. Now, in many sources, they don't actually do it this way that I'm showing you. However, this is an advantageous way of thinking about it and writing it down. And we'll see why in later videos. So what can we integrate over a surface? A vector field. We can think of it as f dot this vector here, which is replacing our dr. It kind of represents aerial projections onto the different coordinate planes, just like the dr represented onto the dx and dy. And then, and we can also write it as a differential two form. Thanks for watching.